Hello, we're going to talk about single slit diffraction. So slit diffraction occur when this opening, there's only one slit. And when this opening, this single slit, it's comparable to the lambda of this monochromatic light. So monochromatic light, so single wavelength light. So when they are very similar, that's when the diffraction occurs. So we're going to look at the first minimum first. So let's look at this situation right here. So this is the minimum, first minimum situation right there. Okay. So this is opening, and D is from here to here, and we're going to break it into two halves like that. So then this one here is D divided by 2. So the actual distance that we consider is right there. Okay, so this delta x is the actual travel distance of this blue ray compared to this ray one. And that is equal to D divided by 2 times the sine theta. And this theta is theta here, and it's also theta over there. So D over 2 sine theta is the delta x. So when does the first minimum occur? It's when this actual travel distance is equal to lambda divided by 2. So when it's lambda divided by 2, which just means 180 degree out of phase. So when they're 180 degree out of phase, then it would be like this. Okay, so this is out of phase. Then this one will cancel this one, and next one will cancel next one. So all of them are lambda over 2 difference in terms of travel distance. So then they will all cancel out. So all light will cancel out in, all the light that goes through this D opening. So then we have D sine theta divided by 2, there's a divide by 2, and there's a lambda divided by 2, so 2 already cancel out. So we have D sine theta equal to lambda. And then we look at this distance here, L, between the screen, this is a screen, and this is the opening. So this is L, and this is Y. This is where the first minimum is. So first minimum. So this is called Y from the center here. So Y divided by L is your tangent theta of, well, I guess I should draw a little better, okay? Y divided by L is your tangent theta here. So now, when theta is very small, sine theta is very approximately equal to tangent theta. And tangent theta is equal to Y divided by L. So we're going to put that Y divided by L into the sine theta location. So we have D times Y divided by L. And now we're going to rearrange the term that dy, so you have dy divided by L is equal to lambda. So he's solving for the Y, so Y is then equal to L lambda divided by D, and which is that one there. So that's how you find the location of the first minimum. Right, now for the first maximum, we're going to divide this opening into 3 pieces now. So you have D divided by 3, D divided by 3, D divided by 3. Right. So we're going to look at the first one right here, and that's your actual distance that we're considering. So actual distance is D divided by 3 times sine theta, just like that. So it's just, and then if we say this actual distance, it's equal to lambda divided by 2 again, right? So then that would make some of the cancellation occur. So that means that this 1/3 will cancel this 1/3. So then you have another 1/3 left. Okay. So then you will have not all the light, but you have 1/3 of the light. So two-thirds of all the lights will cancel. You have 1/3 left. We call that first maximum. So when that occurs, your delta x is equal to lambda by 2. And we're going to put this one into here. So we have D sine theta divided by 3 And then sine theta, we're going to put that y divided by L in again. So y divided by L, and that's equal to lambda divided by 2. So you're solving for the y again. So then y is equal to 3L lambda divided by 2D. Okay? So that's how you find this first minimum and first maximum. I'm going to clear this and give a little drawing for this. On the screen, what you're going to see is, so in the middle, you will see the central maximum. So you will see the central maximum. That's when all the light comes. This is called central maximum. And then that will be your first minimum right there, right? This is your first minimum. And there are two of them. So one is on this side here. So that's also your first minimum. And then you're going to have something that's have 1/3 of light that's not canceled. So that's going to be your first maximum. And same thing on this side here. This will be your first maximum. First maximum there. And you can continue the similar logic for the second minimum. So the second minimum will be there. Second minimum. So for that, you will break it into 1, 2, 3, 4. So then this will cancel this one here. And then let me change the color. And then this will cancel this quarter here. So this quarter cancel that quarter. And then this quarter cancel that quarter, right? So this cancel. And then this two cancel. So then this will be where the second minimum will be. So then this is divided by into 4, right? 4 quadrant when you have this second minimum. So you have 4 quadrant. And then for the next one, which is the second maximum, you then divide it into 5, right? 5 divisions. So then you have 1, 2, 3, 4, 1, 2, 3, 4, 5. So then this will cancel this. And then this will cancel. Let me change the color here. So this will cancel this. So you have 1/5 of light, right? So you have 1/5 of the total lights were left. So then that will become your second maximum. So second maximum has 1/5 of light. And first maximum has 1/3 of light. And second minimum has no lights. First minimum has no lights. And central maximum have one of the 1 lights. Okay, so that is the single slit diffraction. And I'm going to stop there. And until next time, bye-bye now.